March 19th, 1941. The Bay of Biscay. Captain Lieutenant Otto Kretschmer stood on the conning tower of U-boat 99, scanning the dark Atlantic horizon. The night was perfect. No moon. Heavy clouds. Visibility was terrible. To Kretschmer, that meant safety. The Royal Navy couldn't see them. British aircraft couldn't spot them. The darkness had always protected German submarines. For nearly 2 years, U-boats had owned the night. They surfaced after sunset. They charged their batteries. They hunted Allied convoys. Then they disappeared before dawn. The system had worked brilliantly. German submarines were winning the Battle of the Atlantic. Britain was slowly being strangled by the undersea blockade. But something had changed in the past few weeks. U-boats were disappearing. Not just one or two, dozens of them. They would radio their position at night. Then silence. Search parties would find nothing. No wreckage, no survivors, no explanation. German Naval Command was baffled. The submarines were vanishing in conditions where they should have been completely safe, in darkness, in fog, in weather that made visual detection impossible. Kretschmer had heard the rumors. Other U-boat commanders whispered about a new British weapon, some kind of device that could see through darkness. Most commanders dismissed this as superstition. The British couldn't possibly have such technology. Radar existed, yes, but radar couldn't detect small targets like submarine conning towers. Certainly not at night, certainly not in bad weather. The technology simply didn't exist. Kretschmer wasn't so sure. He was one of Germany's most successful U-boat commanders. He had sunk more than 300,000 tons of Allied shipping. He had survived more patrols than almost any other submarine captain. Kretschmer had stayed alive by being careful. He trusted his instincts. His instincts were telling him that something was very wrong. The Atlantic was becoming dangerous in ways it had never been before. The night was no longer safe. What Kretschmer didn't know was that Britain had developed exactly the weapon he feared, a revolutionary radar system that could detect submarines on the surface, even in complete darkness, even in terrible weather. The device was called Type 271 radar. It operated on a wavelength that allowed it to see small targets with unprecedented clarity. British scientists had mounted these radars on escort ships and patrol aircraft. They had created a weapon that turned night into day. German U-boat commanders had no idea they were being hunted by technology they couldn't see, couldn't hear, and couldn't escape. The development of Type 271 radar represented one of the most important technological breakthroughs of the Second World War. It would change the Battle of the Atlantic completely. German submarines that had terrorized Allied shipping would suddenly find themselves the hunted instead of the hunters. The weapon that would save Britain from starvation was not a gun or a depth charge. It was an invisible beam of radio waves that could pierce the darkness and reveal submarines that thought they were hidden. The story of how Britain developed this technology, deployed it in secret, and used it to turn the tide of the Atlantic battle is one of the most remarkable engineering and tactical achievements of the war. The Battle of the Atlantic had been going badly for Britain. By early 1941, German U-boats were sinking Allied ships faster than they could be replaced. The mathematics were terrifying. Britain needed to import 7 million tons of supplies every month to survive. Food, fuel, raw materials. Everything came by ship across the Atlantic. German submarines were destroying British merchant vessels at an unsustainable rate. In the first 3 months of 1941 alone, U-boats sank over 500,000 tons of shipping. If this continued, Britain would be starved into submission within a year. Winston Churchill would later write that the U-boat peril was the only thing that truly frightened him during the war. The Prime Minister understood the mathematics better than most. Britain was an island nation. It couldn't feed itself. It couldn't fuel itself. It depended entirely on imports. If the Atlantic supply lines were cut, Britain would be defeated, not by invasion, not by bombing, but by starvation and economic collapse. The U-boats represented an existential threat to British survival. Everything else depended on winning this battle. The problem was simple but seemingly insurmountable. U-boats operated on the surface at night. They could travel faster on the surface. They could see farther. They could use their diesel engines to charge batteries. Most importantly, they were nearly invisible in darkness. British escort ships had searchlights, but searchlights were useless. You had to know where to point them. By the time a lookout spotted a submarine, the U-boat had already dived. British aircraft patrolled during the day, but U-boats simply stayed submerged until sunset. The night belonged to the Germans. As long as that remained true, Britain would lose the Battle of the Atlantic. German U-boat tactics had been refined through years of combat experience. Admiral Karl Dönitz had developed a system called the Wolf Pack. Multiple submarines would gather near a convoy route. They would wait submerged during daylight. When darkness fell, they would surface and attack. The submarines would coordinate their assaults. They would strike from multiple directions. They would overwhelm the convoy escorts with sheer numbers. By the time escort ships responded to one attack, other U-boats were already launching torpedoes from different positions. The tactics were devastatingly effective. British convoy escorts tried everything they could think of to counter these tactics. They increased the number of escort ships assigned to each convoy. They developed better anti-submarine weapons. They trained their crews in anti-submarine warfare. They established elaborate convoy procedures. None of it was enough. The fundamental problem remained. At night, U-boats could operate with near impunity. Escort commanders couldn't protect what they couldn't see. Merchant ships were being sent to the bottom faster than Britain could replace them. The situation was becoming desperate. British scientists understood that the solution had to be technological. Human eyes couldn't see through darkness, but radio waves could. Radar had been developed before the war. It worked by sending out radio pulses and measuring how long they took to bounce back from objects. The problem was that early radar systems operated on long wavelengths. Long wavelengths could detect large objects like ships and aircraft at great distances, but they couldn't detect small objects like submarine conning towers. The radar beam was too broad. Small targets were lost in the background noise. What Britain needed was radar that operated on much shorter wavelengths. Shorter wavelengths would create a narrower beam. A narrower beam could detect smaller targets with much greater precision. The technology to create short wavelength radar had been developing slowly since the late 1930s. British scientists at the Telecommunications Research Establishment had been working on cavity magnetron technology. This was a device that could generate very high-frequency radio waves, much higher frequency than any previous radar system. The concept was elegant, but extraordinarily difficult to implement. A cavity magnetron used magnetic fields to accelerate electrons in a circular pattern. These accelerating electrons generated radio waves at very specific frequencies. The frequency depended on the precise dimensions of the cavities inside the magnetron. Getting these dimensions exactly right required manufacturing precision that pushed the limits of what was possible in 1940. In February 1940, physicists John Randall and Harry Boot created a cavity magnetron that was far more powerful than anything that had existed before. Their device could generate radio waves at a wavelength of 10 centimeters. This was revolutionary. Previous radar systems operated at wavelengths of 1.5 meters or longer. The new system was 15 times more precise. The implications were staggering. A radar system based on this magnetron could detect objects that previous radars couldn't see. It could distinguish between targets that were close together. It could provide accurate range information. It could, theoretically, detect a submarine conning tower from several miles away, even at night, even in bad weather. But building a prototype in a laboratory was very different from building a working radar system that could be installed on ships and aircraft. The magnetron had to be ruggedized for military use. It had to work in salt spray and rough seas. It had to be reliable enough for combat operations. The entire radar system had to be miniaturized so it could fit on escort vessels. Antennas had to be designed. Displays had to be created. Operators had to be trained. The engineering challenges were immense. Britain was at war. Resources were scarce. Time was running out. The U-boats were winning. A team of scientists and engineers worked around the clock to develop what would become Type 271 radar. The project was given the highest priority. Winston Churchill himself followed the development closely. Churchill understood that Britain's survival depended on winning the Battle of the Atlantic. Winning the Atlantic battle depended on defeating the U-boats. Defeating the U-boats depended on being able to detect them at night. Everything hinged on this new radar system working. The engineering team faced countless challenges. The magnetron generated tremendous heat. It needed cooling systems that wouldn't fail in combat conditions. The radar antenna had to be designed to rotate continuously, scanning the entire horizon. The rotation mechanism had to be precise enough to provide accurate bearing information, but robust enough to work in Atlantic gales. The display system had to show operators where targets were located in a format that could be read quickly under stress. Every component had to be designed, tested, and refined. There was no time for leisurely development. Every week that passed meant more merchant ships sunk and more British sailors dead. The first working prototype of Type 271 was completed in March 1941. The device was installed on HMS Orcus, a Flower-class corvette. The ship was sent out on patrol to test the system in actual combat conditions. The corvette's captain, Commander James Rowland, was skeptical. He had seen promising technologies fail before. He doubted that any radar system could reliably detect something as small as a submarine conning tower in the vast expanse of the Atlantic. But he agreed to test the system thoroughly and report honestly on its performance. The results exceeded all expectations. On its very first patrol, Orcus detected a surfaced U-boat at a distance of over 2 miles. In complete darkness. The submarine had no idea it had been spotted. The radar operator called out the bearing and range. Rowland couldn't believe what he was seeing on the display, a clear, sharp echo from a target that should have been invisible. He ordered the corvette to close on the target at full speed without illuminating it with searchlights. The gap narrowed. 1 mile, half a mile, quarter mile. Only then did Rowland order searchlights turned on. The beams revealed a surfaced U-boat, caught completely by surprise. Orcus closed the distance and dropped depth charges. The U-boat was severely damaged and forced to surface. It was captured. The crew was stunned. They couldn't understand how a British ship had found them in pitch darkness. The U-boat's captain demanded to know how they had been detected. British security officers refused to provide any information. The German prisoners were told simply that they had been unlucky. In reality, they had encountered the weapon that would eventually doom the German submarine campaign. The success of that first patrol proved that Type 271 radar worked, but Britain now faced a different challenge. The technology had to be kept absolutely secret. If the Germans discovered that Britain had developed centimetric radar, they would take countermeasures. German scientists might develop similar technology. German U-boats might change their tactics. They might develop electronic countermeasures. They might coat their submarines with radar-absorbing materials. The advantage would be lost. British security services went to extraordinary lengths to protect the secret of Type 271. Captured U-boat crews were not told how they had been detected. Interrogators were instructed to deflect any questions about detection methods. British sailors were forbidden from discussing the radar in letters home or in conversations ashore. Even many Royal Navy officers were not told the full details of how the system worked. When radar-equipped ships returned to port, the radar antennas were covered with canvas shrouds. Maintenance work on the systems was done below deck, where prying eyes couldn't see. The technology was classified at the highest level. The penalties for discussing it were severe. Production of Type 271 radar began immediately. Britain needed hundreds of these systems. Every escort ship needed to be equipped. Every patrol aircraft needed the radar, but production was slow. The cavity magnetrons were complex to manufacture. Each unit had to be hand-built by skilled technicians. The magnetic components required exotic materials. The precision machining needed specialist equipment. Britain's industrial capacity was already stretched to the breaking point. Factories were building aircraft, tanks, ships, and ammunition. There were never enough resources for everything. The radar production program had to compete with all the other urgent demands of war. Manufacturing the cavity magnetrons required solving problems that had never been encountered before. The copper cavities inside the magnetron had to be machined to tolerances of a few thousandths of an inch. Any deviation would change the frequency and ruin the device. The magnetic materials had to be pure and precisely shaped. The vacuum seals had to be perfect, or the magnetron would fail after a few hours of operation. British manufacturers learned through trial and error. Early production units were unreliable. Many failed after just a few hours of operation. Engineers traced the failures to manufacturing defects and gradually improved the process. By late 1941, production magnetrons were achieving acceptable reliability, but the manufacturing process remained slow and expensive. By the end of 1941, only about 30 Type 271 radar sets had been produced. This was nowhere near enough to equip all the escort ships that needed them. The Royal Navy had to prioritize. The radar sets were installed on ships that patrolled the most dangerous areas, the western approaches, where U-boats concentrated their attacks on convoys approaching Britain, the Bay of Biscay, where U-boats transited between their bases in France and their hunting grounds in the Atlantic. These were the areas where Type 271 radar could have the greatest impact. But even these 30 systems began to have an impact. U-boat sinkings increased. German submarine commanders started reporting strange experiences. They would be on the surface at night in complete darkness. Suddenly, a British ship would appear out of nowhere and attack. The Germans couldn't explain it. The British ships seemed to know exactly where the submarines were. They approached without using searchlights. They came directly at the U-boat's position, as if guided by magic. Only at the last moment would searchlights snap on and guns open fire. By then, it was too late to dive. The U-boat was caught on the surface and had to fight or surrender. Some commanders began to suspect that the British had developed some kind of detection device. Reports filtered back to German naval headquarters. Intelligence officers analyzed the accounts. They noted patterns. British ships seemed able to detect U-boats at ranges of several miles. The detection worked in complete darkness and bad weather. It worked when the sea was rough and when it was calm. Visual detection and sound detection couldn't explain these consistent findings. Something else was happening. But German naval intelligence dismissed these concerns. Their radar experts assured them that radar capable of detecting small targets like submarine conning towers did not exist. The technology wasn't possible with current electronics. The wavelengths required for such precision couldn't be generated with sufficient power. Even if such a radar could be built, it would be too large to install on small escort vessels. The British simply didn't have the technological capability. The reports from U-boat commanders must be explained by other factors. Perhaps the British had broken German codes. Perhaps they had better optical equipment. Perhaps it was just bad luck. But not radar. Definitely not radar. February 1942, the North Atlantic. Captain Lieutenant Erich Topp commanded U-boat 552. Topp was an experienced commander. He had sunk over 30 ships. He understood submarine warfare better than almost anyone in the German Navy. Topp knew that the safest time for a U-boat was at night on the surface. He had operated this way for 2 years without serious problems. But now, Topp was beginning to question everything he thought he knew about submarine warfare. Topp had surfaced his submarine shortly after midnight to charge batteries. The night was dark. Cloud cover was heavy. Visibility was almost zero. By every measure, U-552 should have been completely undetectable. Topp stationed lookouts on the conning tower. They scanned the horizon with binoculars. They saw nothing. They heard nothing. The submarine was alone in the vast darkness of the Atlantic. The diesel engines rumbled steadily, charging the electric batteries that powered the submarine when submerged. Everything was routine. Everything seemed safe. Then, without warning, a British corvette emerged from the darkness less than a mile away. The British ship was heading directly toward U-552. There was no searchlight beam sweeping the water, no star shells illuminating the night. The corvette came out of the darkness on a perfect intercept course, as if it knew exactly where the submarine was. Topp immediately ordered an emergency dive. His crew scrambled below. The lookouts dropped down the hatch. The conning tower hatch slammed shut. The submarine's diesel engines shut down. Electric motors engaged. The boat began to descend. But it was too late. The corvette had closed the distance. Depth charges began to rain down. The explosions were deafening. The submarine shook violently. Light bulbs shattered. Cork insulation broke free from the hull and rained down on the crew. Equipment broke loose from its mountings. Gauges cracked. Water began spraying from pipe fittings that had been jarred loose. The submarine's crew worked frantically to control the damage. They stuffed rags into leaking pipes. They secured loose equipment. They replaced blown fuses. The submarine descended to 300 feet and turned sharply to escape. More depth charges exploded, but these were farther away. The British corvette had lost contact. Topp managed to escape by diving deep and changing course, but he was deeply shaken by the experience. How had the British ship found him? There was no way they could have seen U-552 in that darkness. There was no way they could have heard the submarine. Top had been running on diesels, but those engines were not particularly loud at distance. The sea had been rough enough to mask engine noise. There had been no star shells or searchlight beams. The British corvette had come straight at him as if they knew exactly where he was. It was impossible, but it had happened. Top filed a report with German naval headquarters describing the incident. He stated his belief that the British had some kind of new detection equipment. He couldn't explain what it was or how it worked, but he was certain that visual detection couldn't account for what he had experienced. The British ship had approached in complete darkness on a perfect intercept course. Something had guided them to the submarine's position. German naval intelligence noted the report, but took no immediate action. Top's report was just one of many similar accounts from U-boat commanders, but the pattern was becoming harder to ignore. Top's experience was not unique. Throughout early 1942, German U-boat commanders filed similar reports. Submarines were being detected at night under conditions where detection should have been impossible. British escort ships were finding U-boats with what seemed like uncanny accuracy. They approached without any visible means of detection. They came directly at submarines in total darkness. They launched attacks before U-boat lookouts spotted them. German casualties were rising. Something fundamental had changed in the Atlantic. The night was no longer safe for U-boats. Admiral Karl Dönitz, commander of the German submarine fleet, demanded answers from his intelligence staff. How were the British finding submarines at night? What technology could explain these consistent reports? Were the British using infrared detection devices? Had they developed better optical equipment? Were they using acoustic detection from long range? Had they broken German naval codes? Dönitz wanted concrete answers. His submarine fleet was taking casualties that couldn't be sustained. If the British had developed a new weapon, German tactics needed to change. If it was a technology gap, German scientists needed to close it. But first, they needed to understand what they were facing. German intelligence proposed several theories. Perhaps the British had developed better optical equipment that allowed lookouts to see in near darkness. Perhaps they had trained their lookouts to use peripheral vision more effectively. Human eyes can see faint light better using peripheral vision than direct vision. Perhaps British lookouts had learned this technique. Perhaps the British were using infrared detection devices. Infrared radiation is invisible to the human eye but can be detected with special equipment. A submarine's warm diesel exhaust might be visible with infrared sensors. Perhaps the British had mounted such sensors on escort ships. Perhaps the British had developed long-range acoustic detection equipment. Hydrophones could detect submarine engine noise from considerable distances. Perhaps the British had developed better hydrophones and better signal processing. Perhaps they could hear U-boats at ranges of several miles. Perhaps the British had broken German naval codes. If the British could read encrypted messages, they would know where U-boats were operating. They could position escort ships to intercept submarines in areas where they were expected to surface. None of these theories fully explained what was happening. Better optical equipment couldn't account for detection in zero visibility. Infrared detection was possible but had severe range limitations. The technology of 1942 couldn't detect infrared radiation at ranges of several miles. Acoustic detection was limited by the noise of the detecting ship's own engines. British escort ships making high speed to intercept a submarine would generate too much noise for their hydrophones to hear anything. Code breaking might explain why British ships were in the right area, but it couldn't explain how they found individual submarines with such precision. German scientists were consulted. They assured Naval Command that radar capable of detecting small targets like submarine conning towers did not exist. The wavelengths required for such precision were impossible to generate with sufficient power. Radar worked by sending out radio pulses and measuring the time it took for those pulses to bounce back from objects. The accuracy of radar depended on the wavelength. Shorter wavelengths provided better resolution and could detect smaller objects, but shorter wavelengths required much more power. The power requirements increased dramatically as wavelength decreased. At wavelengths short enough to detect a submarine conning tower, the power requirements would be enormous. No radar transmitter that powerful could be built with current technology. The technology simply wasn't possible. German intelligence was wrong. Not only was the technology possible, it was already being deployed across the Atlantic. By mid-1942, over 100 British escort ships had been equipped with Type 271 radar. Production was accelerating. New improved versions were being developed. Britain was winning the technological race, and the Germans didn't even know they were in a race. The impact of Type 271 radar on U-boat operations was devastating. German submarines that had previously operated with relative impunity were now being hunted with precision. U-boat losses increased dramatically. In the first 6 months of 1942, 21 U-boats were lost. Many of these losses were directly attributable to Type 271 radar. British escort commanders learned to use the radar with increasing skill. They would detect a surface submarine at long range. They would approach without using searchlights or giving any indication they had spotted the target. They would plot an intercept course that accounted for the submarine's movement. Then, at close range, they would illuminate the submarine with searchlights and open fire. By the time the U-boat crew realized they had been detected, it was too late to dive and escape. The tactical advantage provided by Type 271 radar was enormous. British escort commanders could now hunt submarines at night with the same effectiveness as during daylight. They didn't have to rely on visual detection. They didn't have to wait for submarines to give away their position. The radar allowed them to detect U-boats at ranges of 3 to 5 miles in good conditions. This gave them time to maneuver into position. It gave them time to coordinate attacks with other escorts. It allowed them to catch submarines on the surface where they were most vulnerable. The psychological impact on German submariners was profound. U-boat crews had always known that submarine warfare was dangerous, but they had believed that the night provided safety. Now that assumption was shattered. German sailors no longer felt safe on the surface at night. Lookouts scanned the darkness with mounting anxiety. Every shadow might be a British escort ship closing for the kill. Every sound might be the death charges falling. The stress of night surface operations became unbearable for many men. Some commanders began to question whether surfacing at all was worth the risk. But submarines had to surface regularly to charge batteries and refresh air. There was no alternative. U-boat crews began to feel hunted. Morale declined. The men who had once been the hunters were now the prey. Admiral Dönitz recognized that something fundamental had changed in the Battle of the Atlantic. He issued new instructions to U-boat commanders. Submarines were to spend as little time as possible on the surface. They were to surface only when absolutely necessary to charge batteries. They were to dive immediately if anything suspicious was detected. Lookouts were to be doubled during surface operations. Every precaution was to be taken. The new instructions acknowledged that the night was no longer safe, but they couldn't explain why. Dönitz still didn't know about Type 271 radar. He was issuing orders to counter a threat he didn't fully understand. But these measures were largely ineffective. Type 271 radar could detect a submarine before the submarine's lookouts could see the British ship. The U-boats were fighting a battle they couldn't win with the tactics and technology they had. German submariners began to feel that they were at the mercy of an enemy that could see them but couldn't be seen. It was a terrifying reversal of the situation that had existed for the first 2 years of the war. German naval intelligence finally began to take the situation seriously in late 1942. They analyzed reports from returning U-boat commanders. They interrogated survivors from sunken submarines. They examined captured British equipment when possible. They studied photographs of British escort ships taken by German reconnaissance aircraft. Slowly, the pieces began to fit together. British ships had new antenna arrays mounted on their masts. The antennas were smaller than traditional radar antennas. They were shaped differently. They rotated continuously. This suggested some kind of radar system. But what kind? German intelligence officers contacted their counterparts in German scientific research. Could the British have developed radar that operated on shorter wavelengths than previously thought possible? German scientists reviewed the physics. They examined the engineering challenges. They consulted their own radar development programs. Gradually, reluctantly, they began to accept that it might be possible. If the British had made breakthroughs in high-frequency electronics, they might have developed centimetric radar. Such a radar could detect small targets. It could provide accurate range and bearing information. It could explain everything the U-boat commanders were reporting. The realization came too late. By the time German intelligence understood what they were facing, Hundreds of Type 271 radar sets had been deployed. Britain had gained a decisive technological advantage. German scientists began working on countermeasures. They developed radar detection equipment that could warn U-boats when they were being illuminated by centimetric radar. The device was called Naxos. It could detect radar transmissions and alert submarine crews that they were being tracked. But Naxos had limitations. It could only detect radar at shorter ranges than the radar itself could detect the submarine. By the time Naxos warned a U-boat crew, the British ship was already closing for the kill. The warning gave submarines a few extra seconds to dive. Sometimes that was enough to escape. Often it wasn't. German scientists also developed radar-absorbing coatings for submarine conning towers. The coatings were made of carbon and rubber. They absorbed radio waves rather than reflecting them. A submarine with this coating would have a much smaller radar signature. It would be harder to detect. The coatings were tested and found to be effective, but applying them to operational submarines was difficult. The coating had to cover all the metal surfaces on the conning tower. It had to be maintained because it degraded in salt water. Many U-boat commanders were skeptical that the coating would make enough difference to justify the effort. Some submarines were equipped with the coating. Others weren't. The program was never fully implemented. Germany experimented with different submarine designs that would be harder to detect by radar. They developed streamlined conning towers with fewer protrusions. They experimented with coating the entire submarine hull with radar-absorbing material. They designed submarines that could spend more time submerged and less time on the surface. The Type 21 U-boat, developed late in the war, incorporated many of these features. It had a streamlined design. It had much larger batteries that allowed it to remain submerged for extended periods. It was much faster underwater than previous submarines. The Type 21 was a revolutionary design that might have challenged Allied supremacy if it had been available in large numbers earlier in the war. But all of these responses took time to develop, test, and deploy. Meanwhile, British escort forces were becoming increasingly effective at hunting submarines. The Type 271 radar was being continuously improved. Engineers developed versions with better range and resolution. They improved the displays to make them easier to read. They developed automatic tracking systems that could follow multiple targets. By 1943, the radar had evolved from an experimental prototype into a mature and reliable system that gave British forces an overwhelming advantage. The turning point in the Battle of the Atlantic came in May 1943. That month, German U-boats lost 41 submarines. This represented more than 10% of the entire operational U-boat fleet. The losses were catastrophic. Many of the submarines were lost to attacks that began with Type 271 radar detection. British escorts would find submarines at night. They would coordinate attacks with multiple ships. They would drop depth charges in patterns that gave submarines little chance of escape. The casualty rate was unsustainable. Admiral Dönitz was forced to make a decision that effectively ended the U-boat campaign. On May 24, 1943, he ordered German submarines to withdraw from the North Atlantic convoy routes. For the first time since the war began, British merchant shipping could cross the Atlantic without facing massive submarine attacks. The withdrawal was supposed to be temporary. Dönitz planned to resume operations once German submarines had been equipped with better defensive equipment, but the German submarine force never fully recovered from the losses of May 1943. The Battle of the Atlantic had turned decisively in Britain's favor. Type 271 radar had not single-handedly won the Battle of the Atlantic. Other technologies and tactics played important roles. Improved sonar allowed escort ships to track submerged submarines more effectively. Better depth charges that could be set to explode at greater depths made it harder for submarines to escape by diving deep. Long-range patrol aircraft based in Iceland and Canada closed the air gap in the mid-Atlantic, where submarines had previously operated without air cover. The breaking of German naval codes allowed the Allies to route convoys away from known U-boat positions. Improved convoy procedures and better coordination among escorts made attacks more difficult. All of these factors contributed to the Allied victory. But Type 271 radar was the technology that fundamentally changed the tactical balance. It was the weapon that took away the U-boat's greatest advantage. For 2 years, German submarines had owned the night. They could surface after dark and operate with relative safety. British escorts couldn't find them. British aircraft couldn't spot them. The darkness was their shield. Type 271 radar shattered that shield. It turned night from a German advantage into a German vulnerability. Once submarines could be detected at night, their tactical advantage evaporated. They became targets instead of hunters. The psychological impact was as important as the tactical impact. German submariners lost confidence. They no longer felt safe. The Atlantic became a place of terror rather than triumph. The technological race between Britain and Germany continued throughout the remainder of the war. Germany developed the Schnorkel, a breathing tube that allowed submarines to run their diesel engines while remaining submerged just below the surface. This reduced the need to fully surface. Submarines with Schnorkels could charge batteries while presenting a much smaller radar target. The Schnorkel was an effective countermeasure, but it had limitations. Submarines running on Schnorkel had to move slowly. The breathing tube created a wake that could be spotted visually or by radar. The Schnorkel didn't make submarines invisible. It just made them harder to detect. Germany also accelerated development of the Type 21 submarine. This design represented a fundamental rethinking of submarine warfare. Previous submarines were really surface ships that could dive to escape danger. They were optimized for surface operations. They were faster on the surface than submerged. Their batteries could only power them underwater for short periods. The Type 21 was designed as a true submarine. It was faster underwater than on the surface. It had enormous battery capacity that allowed it to remain submerged for days. It had a streamlined hull designed for underwater speed. It was a revolutionary design that anticipated modern submarines. But the Type 21 came too late to affect the outcome of the Battle of the Atlantic. The first operational boats didn't enter service until April 1945, just weeks before Germany surrendered. Only a handful were completed before the war ended. If Germany had developed this design 2 years earlier and built it in large numbers, the Battle of the Atlantic might have gone very differently. But German industrial capacity was stretched thin by fighting on multiple fronts. Resources that might have gone into submarine production were diverted to other priorities. The Type 21 remained a technological achievement that never had the chance to prove itself in combat. British scientists continued to improve centimetric radar throughout the war and after. They developed versions that operated at even shorter wavelengths. 3-centimeter radar provided even better resolution than 10-centimeter systems. They developed airborne radar that could be fitted to patrol aircraft. The ASV Mark III radar allowed aircraft like the Lee Light Wellington to hunt submarines at night. The combination of radar detection and powerful searchlights made night flying patrols devastatingly effective. They improved the displays used by radar operators. Early displays showed raw radar returns that required skilled interpretation. Later displays incorporated signal processing that highlighted targets and suppressed clutter. They developed automatic tracking systems that could follow multiple targets simultaneously and predict their future positions. By the end of the war, centimetric radar had evolved from an experimental prototype into a mature and reliable technology that was standard equipment on Allied ships and aircraft. The lessons learned from developing Type 271 would influence radar design for decades. The cavity magnetron developed for this radar became one of the most important electronic components of the 20th century. Virtually all microwave technology can trace its origins back to the work done by British scientists in 1940 and 1941. The impact of Type 271 radar extended far beyond the Battle of the Atlantic. The technology developed for detecting submarines was adapted for many other purposes. Centimetric radar was used for aircraft navigation in bad weather. Ground mapping radar allowed bombers to find targets through clouds. Fire control radar guided naval gunfire with unprecedented accuracy. Air intercept radar allowed night fighters to detect and track enemy bombers in darkness. Search radar allowed ships to detect aircraft and surface vessels at long range. The applications were almost limitless. After the war, centimetric radar technology found widespread civilian applications. Weather radar uses centimetric wavelengths to detect rain and storms. The radar displays that meteorologists use to forecast weather are direct descendants of Type 271. Air traffic control radar uses similar technology to track aircraft and ensure safe separation. Marine navigation radar helps ships avoid collisions in fog and darkness. Police speed radar uses centimetric wavelengths to measure vehicle speeds. Even microwave ovens are based on cavity magnetron technology. The magnetron in a microwave oven is essentially the same device that was developed for Type 271 radar. It generates high-frequency radio waves that heat food by exciting water molecules. The men who developed Type 271 radar received little public recognition during the war or immediately after. Their work was classified at the highest levels. Security restrictions prevented them from discussing their achievements. Many of the scientists and engineers who contributed to the project worked in complete anonymity. John Randall and Harry Boot, who invented the cavity magnetron, were largely unknown outside scientific circles. The engineers who turned laboratory prototypes into reliable military equipment received no public acknowledgement. The technicians who manufactured the complex components worked without recognition. The radar operators who used the equipment in combat were forbidden from discussing it. The whole project remained secret for years after the war ended. Gradually, as security restrictions were relaxed, the story of Type 271 began to emerge. Military historians researching the Battle of the Atlantic recognized the radar's crucial role. Scientific historians documented the technological breakthroughs. Memoirs from participants began to appear. By the 1960s and 70s, the full story was becoming known. John Randall and Harry Boot received belated recognition for their invention of the cavity magnetron. The scientists and engineers who developed the radar system were finally acknowledged, but many of the people who contributed to the project had died without ever receiving public recognition for their work. The German submariners who faced Type 271 radar in combat were veterans who had survived some of the most dangerous combat of the war. These were not novices. They were highly skilled professionals who had been trained to operate in conditions where mistakes meant death. Many had years of combat experience. They had developed tactics and techniques that had been devastatingly effective. The fact that so many of them were defeated by a technology they couldn't see or understand speaks to the revolutionary nature of centimetric radar. This was not an incremental improvement. This was a fundamental change in naval warfare. It represented the triumph of scientific innovation over traditional military methods. Today, more than 80 years after Type 271 radar was first deployed, the technology seems primitive by modern standards. Modern radar systems operate at multiple wavelengths simultaneously. They use sophisticated signal processing to extract information from radar returns. They can track hundreds of targets simultaneously with computer assistance. They can distinguish between different types of targets based on radar signatures. They can see through weather and darkness with far greater clarity than Type 271 could. But in 1941, Type 271 represented the cutting edge of technology. It was a weapon that changed history. The development of Type 271 radar demonstrates what can be achieved when scientific innovation is driven by urgent necessity. Britain in 1941 was fighting for its survival. The U-boat campaign was succeeding. Conventional weapons and tactics were proving inadequate. The nation desperately needed a technological breakthrough. British scientists and engineers delivered that breakthrough. They developed technology that the enemy believed was impossible. They deployed it in absolute secrecy. They refined it continuously based on combat experience. They used it with devastating tactical effectiveness. The result was a weapon that helped turn the tide of the Battle of the Atlantic from German victory toward Allied triumph. The story of Type 271 radar is ultimately a story about the power of innovation in the face of existential threat. It's a story about scientists and engineers who worked around the clock to develop technology that could save their nation. It's a story about the importance of maintaining technological superiority in warfare. It's a story about the courage of sailors who used new and untested equipment in combat. It's a story about the defeat of an enemy who believed he understood the rules of warfare, but discovered that those rules had changed. The U-boat commanders who once owned the night learned that technology could turn darkness into light and safety into vulnerability. They discovered that in modern warfare, the side with better technology and better intelligence would usually prevail over the side with better tactics and more experienced personnel. It was a lesson that Germany learned too late to change the outcome of the war. Type 271 radar was one of the weapons that ensured that Germany would not win the Battle of the Atlantic. and without winning that battle, Germany could not win the war.